Hi everyone, this is our first calculus lesson, and we're going to begin by talking about rates of change because that's what calculus is all about. So I can remind you that a rate is a ratio that compares two quantities with different units of measure. And you've used rates before in math and in physics. So let's begin with a few examples. If we say that a pilot flew his plane 225 miles in 45 minutes, what was his speed per minute? Well, his speed per minute would be the distance, 225 miles, divided by the time, 45 minutes, and that is a rate. It's a comparison or a quotient, a ratio of two quantities with different measures. So if you do 225 divided by 45, you get that this pilot is flying at 5 miles per minute. That is his rate. Speed is a rate. The next one says a 3-pound loaf of bread costs $5.25. At the same rate per pound, how much would a 1-pound loaf cost, right? So we take our 3 pounds and that costs $5.25. So we want to know how much would 1 pound cost. We take the $5.25 and compare it to 3 pounds. Remember, a division is a compare, right? So 525 divided by 3 gives us $1.75 for 1 pound, right? And that's the rate per pound for that example. The next one, we're given a rate. Maria earns $6.50 per hour. That's her pay per hour. That's a rate. How much does she earn working 15 hours? Well, we take this rate of $6.50 for each hour. We multiply it by 15 to get how much her total is, right? So we get 97.5 is how much she would make in 15 hours. So these are just some examples of rates as you've already used them before. And in all of these examples, you can see that we are assuming something. We're assuming that the rate stays the same. Maria earns $6.50 for the first hour and the second hour and the third hour. And if she were to work half an hour, then she would earn $3.25, right? So we're assuming that this rate stays constant the whole time. The pilot is assumed in this example to be flying at the same rate throughout the 45 minutes. And the bread, the first pound costs the same as the second pound, and so on. So on all these examples, the rate stays the same, or we say in math that the rate is a constant, it doesn't change. That's like saying that we are climbing a mountain with a constant slope. And we're going to see that slope and rate are basically the same thing. So the thing is that that's not how the real world usually works. In the real world, rates are constantly changing. If you climb a mountain, you're going to have different slopes at different places. If you're flying a plane, you're not going to fly at exactly the same speed every instant. So calculus is the math that allows us to move from this constant rate situation to a changing rate situation. Calculus is the math that allows us to model the real world with rates that are changing every instant. So that's a very brief intro to what the entire field of calculus is about. So let's now focus on one specific type of rate, which is a rate of change of position, right? That tells us how fast is something moving. When you look at how fast a car is moving, here's a little car, right? Has 4 wheels. It's at this place or position at time t equals 0, and now it's over here at time t equals 10 seconds or minutes, whatever. So the position of this car has changed, and how fast the position changes tells us how fast the car is moving. So in math and in physics, we call the rate of change of position, well, we use two words, and I'm going to explain the difference. Most simply, we say the rate of change of position is a speed, right? And the average speed, you've seen this formula before. You say speed is equal to distance divided by time, right? That's what you already have heard. Now, velocity might be a word that you have not heard before, or if you've heard it, you may not know exactly what it means. It's very simple. Velocity is just speed with a sign, right? So think of it as if you're moving, if this car is moving forward at 50 miles per hour, right? Then the speed is 50 miles per hour and the velocity is also 50 miles per hour. If this same car were moving backward at 50 miles per hour, then the speed would still be 50 miles per hour. The velocity would be negative 50 miles per hour. That's why we say that speed is a scalar. It does not involve direction. Velocity is a vector. It involves direction. So in math, we use a sign, plus or minus, to indicate direction. Okay, so now let's look at average velocity from a graph. Well, I already mentioned to you that slope, right, is basically rate. When you think of climbing a mountain, the slope tells you like how fast your horizontal position is changing, right? So in these kind of problems where you're given a graph of position, notice position is on the y-axis and time is on the y-axis. Position is in meters, time is in seconds. Always check that out. Make sure you understand your graph. It's very simple. In average velocity, right, is going to be a constant. It's going to be just one number, and it's going to be depending on which part of the graph you're in, it's the slope at each part of the graph. So in this first stretch right here, we'll color this in blue, we're moving forward. The position is increasing, right? Position is going from 0 to 5 to 10 to 15 and so on. So we're moving forward. Velocity is going to be positive. You can see that the slope of that line is positive, and you just have to find the slope. It's the rise over the run, 25 divided by 2, or in other words, the velocity for this stretch of time is going to be 12.5 meters per second, 25 divided by 2. When we get to the top here, we see that position is not changing. If your position is not changing, then clearly your speed is 0, your velocity is 0, right? So the velocity is 0 meters per second in this stretch of time from 2 to 6 seconds. We come over here, you can see that the slope of this graph is now negative, right? So the slope became negative here. That means the car or whatever this is that's moving is moving backward. And you can see that the position here is 25 at t equals 6, and the position is 15 meters at t equals 8, right? So remember, if you're thinking of position along an axis, along an x-axis, right, this thing is moving in a straight line. It's moving back and forth. When the slope is negative, the velocity is negative. So the velocity here is going to be negative, and the rise over the run is it's really 15 minus 25, right, divided by, that's y2 minus y1 divided by x2 minus x1. So we're going to get negative 10 divided by 2, or negative 5 meters per second. And then in this stretch over here, again, we're not moving, so position is constant, velocity is 0. And then in this last stretch here, we're again moving backwards, right? And you can just find the slope of that line. And you can use any 2 points, right? I might use this point right here and this point here. and see that the change in y, you always want to do the second point minus the first point. So the change in y is going to be 0 minus 15, and that's the rise, and the run is 14 minus 11, right? So 14 minus 11 is 3. So I get negative 5 meters per second. Same thing as I got in this other stretch here. And you can see these two lines are parallel, so you would expect that. So that's how you find average velocity from a graph. Okay, next we want to know how to find average velocity or speed from a table, right? So in this case, a motorcyclist accelerates from rest along a straight path. Accelerates means the speed is increasing, the velocity is increasing. We're just assuming this guy is going forward the whole time, right? So in this problem, I'm using speed and velocity interchangeably because you can see the position is just seems to be increasing the whole time, right? So that's why I'm saying that. Now, selected values of his position S from the starting point are given in the table, right? So here's S and here's time. At time t equals 0, his position is 0, right? So think of it as you have your axis here. Time t equals 0, he's here at 0. At time t equals 1, he's at 4.9. At time t equals 2, he's at 20.6. You can already see he went much faster in the in the second than he did in the first second, right? And so, he's here on his bike. I don't know how to draw a bike, but it's accelerating like that. Okay, so if we're finding the average velocity for the time interval 2 to 4, all we have to do is do a rise over run calculation between those 2 points, right? So for part A, we would say his average velocity in this time interval will be y2 minus y1 divided by x2 minus x1. This is y2, this is x2, this is y1, this is x1, right? Or sometimes we'll say y2 and t2 for the second time and t1 for the first time. So you just do this little calculation and you get, let's see, 79.5 minus 20.6 divided by 2. And that's 29.45 meters per second would be his average velocity between time t equals 2 and time t equals 4. If you were to do the same thing between 4 and 6, well, now you're looking at these 2 times. And so you would do average velocity for B is going to be 176.7 minus 79.5 divided by, again, 6 minus 4, which is 2. So this works out to be 48.6 feet per second. I made a mistake back here. I'm sorry. Going to correct this. This first velocity should have been in feet per second, right? Because the position is given to us in feet. So we can see that on average, he's traveling faster in 4 to 6 time frame than he is from 2 seconds to 4 seconds. And that makes sense based on what the question told us about accelerating. Accelerating means his speed is increasing. Okay, so we now know how to do average velocity from a graph and also from a table. And you'll notice in both cases, we're just doing a rise over run calculation. Okay, now we need to know how to do the same thing from an equation. So example 3 says a rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of the fall? Assume that the distance the rock falls is given by y is equal to 16t squared. So if we're looking for average speed, then what we need is a rise over run calculation. In this case, the question said speed. The rock is moving downwards, right? So the velocity would be negative, right? The speed is just always positive, right? So speed is really the absolute value of the velocity. Speed is always going to be a positive number, right? So in this case, we know that the velocity would be a negative number, but the question said average speed, so we're just going to take the absolute value of our velocity. So it's an average, so again, it's going to be just a rise over run calculation or a distance over time calculation. We know that at the beginning, it hasn't fallen at all, right? The distance is, you would go t equals 0, that would be the beginning, or it said the first 2 seconds, right? So your t1 is 0, and your y1 is 16 times 0 squared, or 0. Your t2 is 2 seconds, and your y2 is 16 times 2 squared, or 64, right? Okay, so our average speed is just going to be the distance traveled, which is 64 minus 0, right, divided by the time, which is 2 minus 0. So the average speed is 32 feet per second. I just want to make a quick comment about velocity, right? In this problem, we did average speed, so we just needed the distance. We didn't care whether the first position was higher than the second or lower than the second. We just took the distance divided by the time, right? When you talk about velocity, if we wanted average velocity, then you'd have to think like this. You would think, we don't really know the height of this cliff, right? But it's somewhere, say it's 100 feet, you can assume that. We know that the distance fallen is 64 feet in the first 2 seconds, right? So that means that we're down by 64. So we're now at 36 feet, right, at t equals 2. So t equals 0 is up here, t equals 2 would be here. And so really our calculation would become 36 minus 100 over 2 minus 0, or negative 64 over 2, negative 32 feet per second, right? So that would be average velocity. Okay, so the key takeaway from all of this is that the average rate of change, we've been looking at position, and therefore it's the average rate of change of position or velocity that we've been talking about. But in general, we could do this for any quantity. The average rate of change of any quantity is given by this difference quotient. We call this a difference quotient. It's the rise over run calculation. Rise, y2 minus y1, over run, x2 minus x1, right? Sometimes we write it as f of x2 minus f of x1 over x2 minus x1, but this just means y2 and y1, right? Sometimes we use this delta symbol. Delta means the change, right? So the change in y, that's y2 minus y1, over the change in x. That's another way to say the same thing. So all of these things are formulas for the average rate of change, and this one is important to remember. The formula is important to remember, as is this way of talking about it as a difference quotient, right? So this is important. Okay, now we come to calculus, instantaneous velocity. We know that if you think of dropping something from a cliff, or just even dropping your pencil on the ground, the pencil or the rock is not going to travel at the same speed the whole time. We know that the velocity of objects is going to increase as it falls down to Earth. The closer you are to Earth, the faster and faster the rock is going to be moving. So in this question, we're asked, for the rock falling from the cliff, find the velocity of the rock, not just average, not just saying, well, it's falling at this same 32 feet per second the whole time, because we know that's wrong. We're asked to find the velocity of the rock at the instant. That means at the specific moment. An instant means a moment in time at t equals 2 seconds, at precisely that moment. So let's just remind ourselves that an instant means a moment, a specific moment in time, right? So we don't have an interval of time like we had for the average calculations. We are at an instant. Okay, so instantaneous velocity or speed is equal to the velocity or speed at an instant in time, right? So we want to remember that this word instantaneous refers to a specific instant. So the first question is, why can't I just do what I was doing above there? Just do this AROC formula. Well, the problem is that at a specific instant, if you try to do y2 minus y1 over t2 minus t1 and everything is at t is equal to 2 seconds, you're just going to get 0. The rock hasn't moved at 2 seconds and the time hasn't changed. So you're going to get 0 over 0. And you should remember that 0 over 0 is not 0. It's not a DNE. It's can be it's an indeterminate form. It doesn't allow us to get an answer. Okay, so the question then is, how do we get an answer? How do we know how fast is that rock traveling at 2 seconds? What is the instantaneous velocity? Well, we do that by what we call a limit calculation, and that's why limits are so important in calculus, that we're going to spend a whole month on limits, right? But the whole reason for this is because that is the way in which we're going to find our instantaneous velocities. Okay, so the way we approach instantaneous velocity is that let's draw a picture. We've got, the position of this rock. We know that it goes like y is equal to 16t squared. That's the distance, right? So wherever we're starting from, say it's 100 feet, right? The position s would be 100 minus 16t squared, right? Because 16t squared is the distance that we've traveled. So it's like a parabola, right? This is a downward facing parabola, and it's think of it this way: negative 16t squared plus 100 has a y-intercept of 100, and then from there it's this downward facing parabola like this, right? And we could even calculate the root here and when it's going to hit the ground. And that would actually be like saying, when is the position, this right here, this ground is position y is equal to 0, right? So we could just set this negative 16t squared plus 100 equals 0. So t squared is equal to 6.25, and t would come out to be 2.5, right? So we know that when time is equal to 2.5, this rock is going to hit the ground. And what we did in the first, in the average example above, was we said, well, we're going to go from 0 to 2 seconds, right, which is somewhere here, and we just did this rise over run calculation, and that's what we got as negative 32 feet per second. So if we want to know what is the rate of change right at t is equal to 2, what is the speed at 2, what we can do is we can start doing average calculations for times that are closer and closer to t is equal to 2 seconds, right? I could say, instead of starting at 0, let me go from 1 to 2 seconds and calculate the slope of that line. And then let me go from 1.5 to 2 seconds. And then let me go from 1.9 to 2 seconds, right? And keep on calculating the slopes of these lines and see what happens, right? So when we do that, we find that if you look at the average speed over shorter and shorter time intervals, right? If I go from 1 to 2, then I'm going over a total time of 1 second to the left of 2, right? And I get that my average speed would be 80 feet per second. If I go from 1.9 to 2.1 second, then I get that my average speed is 65.6 seconds. 65.6 feet per second. This is in feet per second, and this is the time interval that I'm using for my average calculation. So I'm calculating my average over smaller and smaller time intervals. And when I write down these numbers, you're going to see that something kind of interesting happens, is that as you calculate the average over shorter and shorter time intervals next to t is equal to 2, the number for the speed gets closer and closer to 64 feet per second. You can see there's a trend here, right? This looks like if I kept on going, making that interval shorter and shorter and shorter, then I would get an answer, a limiting answer of 64 feet per second for the speed, or negative 64 feet per second for the velocity, right? So that is basically the huge takeaway for now, is that the instantaneous velocity is going to be defined as the limiting value of the average velocity, right? Instantaneous rate of change is the limiting value of the average rate of change. Instantaneous rate of change, I'm going to abbreviate that as IROC. That's not a college board abbreviation, so don't use that on your AP exam, but I do use this. IROC is the limit of the AROC, right? You see that difference quotient there, as x2 approaches x1, right? So what does that mean? That means as x2 approaching x1 means the 2 points are getting closer and closer, right? So you can go on making this average calculation for closer and closer and closer time intervals. And what is going to happen is you're going to get to a limiting value, and that's the instantaneous rate. Something interesting to note is that as you go on making those 2 points closer and closer, what used to be a secant line, right? Secant line means 2 points on a curve and they're connected, right? 2 points on a curve, they're connected. 2 points on a curve connected. That becomes more and more like the tangent line. A tangent line is a line that just touches a curve at one point and goes in the direction of the curve. The secant line is the line that connects 2 points on the curve. So we can see that the AROC graphically is the slope of a secant line, and the IROC is the the slope of a tangent line, right? So that's also a very important takeaway. Okay, so that's really all we're doing for today. Let's summarize with our takeaways. A rate tells us how fast something is changing any quantity, right? It can be your position, it can be the price of a stock, it can be the volume of water flowing in a river. It can be the gas that you're pumping into your gas tank. It can be anything, but a rate tells us how fast something is changing. Calculus allows us to model real world situations, right, where the rate of change is not constant. The rate of change is not the same. It keeps on changing. Velocity means the rate of change of position. Average velocity is equal to y2 minus y1 over x2 minus x1. On a linear graph, AROC is the slope of the graph. AROC is equal to the IROC for a linear graph. On a nonlinear graph, AROC is the slope of a secant line to the graph between 2 points. There are 2 points involved in an AROC. On a nonlinear graph, IROC is the slope of a tangent line. So just notice that for an IROC, we're talking about one particular point, right? And we're just finding the slope of that line, that linear tangent line that touches that particular point. The formula for a difference quotient, we already set it up there. I'll say it another way here. F of x2 minus f of x1 over x2 minus x1. And then, very important, the fundamental basis of calculus is this insight that the instantaneous rate of change, right? IROC means instantaneous at a particular instant. That is the limit or the limiting value of the average rate of change, right? In other words, the instantaneous rate is the same difference quotient, but as x2 gets closer and closer and closer to x1, and really we have to do this limit calculation that we saw in our formula before, right? So this right here would be the instantaneous rate of change. So, and then we talked about, of course, how to find the average rate of change from a graph and from a table and from an equation. So, hope you enjoyed your first lesson of calculus.